Hello everyone, welcome to this video in the Decision Trees from Scratch series. Today I am very excited to make this video because this will be a hands-on tutorial on building an entire classification tree in Python from start right till the end. We will learn everything along the way, and I'll also write down many things on the whiteboard. Towards the end, we will be building the classification tree for a real world and an highly impactful problem. Before we start, I just want to give the credits to this notebook which you are seeing right now and this video to Joshua Stermer from the Stats Quest channel. uh, if you have not been to that channel, it's one of the best channels for many things related to uh, decision trees, etc. And I have borrowed this notebook from there. So just giving credits at the start. Let's get started now. Essentially, our main aim in this lecture is to use decision trees to predict whether a patient will have heart disease or not. Previously, if you're following this series, we have conducted 5 to 6 lectures on understanding basics of classification trees and regression trees, such as Gini impurity, entropy, pruning, etc. Now, all of these things will come together, and I will show you how a machine learning engineer thinks about solving a real life problem using decision trees. So, first, it's very important for us to understand the problem itself before even coming to solving it. So, let me tell you where the data set is collected from. So, it's a heart disease data set and it's collected from this UC Irvine machine learning repository. They have a huge number of popular data sets. So, the heart disease data set, the way the data set is structured is that the data was collected from Cleveland, I think, in the USA, and there were a number of patients who came in for diagnosis and for understanding whether they do have this disease or not. And while the course of this research proceeded, a large data set was created for all of these patients. This data set is actually documented in a 1989 paper, which is titled International Application of a New Probability Algorithm for the Diagnosis of Coronary Artery Disease. For the publication of this paper, this dataset was collected, and now we are using this dataset for machine learning tasks. So let's understand the dataset itself. But before that, I just want to explain you the visual representation of the problem which we are trying to solve. Imagine a person. That person has many attributes such as age, what's their age, what's their sex, are they male, are they female, then a number of other attributes which we'll be coming to in a moment. But overall, if you count these number of attributes, there are 13. So let me count it: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 13 different attributes for every single patient which we are going to be looking at. Based on these attributes, we have to feed these attributes and the data associated with these attributes to the decision tree model, and then the final goal which we have is to predict whether any new patient, not just the people whom we have used for training, but let's say if any new person comes and we collect these attributes for the new person, can we predict whether that new patient has a heart disease or they do not have a heart disease? That's the main problem which we are trying to solve. So even before moving further with any machine learning project, it's actually very important for everyone to know the problem itself and the objective which we are trying to achieve. I hope everyone is on the same page with me until this point. Now let's move to the next step. The step number one of this project is going to be understanding the data set itself. So let's look at the data set again in more detail. And I have actually asked ChatGPT to give me descriptions of each of these different variables. So here is what ChatGPT answers. I think it's very important to understand the variable meaning. Many people just proceed with an ML problem without knowing what these variables represent, but I think it really helps to debug issues such as categorical variables, non-categorical variables. It makes it much easier, and it's always good if you have the intuition. It makes you interested more in the problem. The first variable is the age of the patient in years. It's very simple to understand. The second variable is the sex, which is the gender of the patient. So we have 1 for male and we have 0 for female. The third variable is called CP. This is for quantifying the type of chest pain the patient experiences. So this is actually on a scale of 1 to 4 in the data set which we have. Higher indicates more typical angina. So you don't need to know what angina means, but just know that CP is a type of chest pain which the patient experiences, and it's on a scale of 1 to 4. 4 means that the chest pain is the highest, 1 means that the chest pain is the lowest. Rest BP is the patient's resting blood pressure, which is measured in millimeters of mercury. The variable CHOL, which is called, is the patient's serum cholesterol level, which is also measured in milligrams per deciliter. Then FBS is the patient's fasting blood sugar level, but it's not just that level. The FBS is actually a categorical variable which indicates if the patient's fasting blood sugar is above 120 mg per dl. If it's above, it's not very good. As we know, it can lead to more symptoms of diseases. So this variable takes values of either 1 or 0. If it's 1, it means the patient's fasting blood sugar is more than 120. If it's 0, is less than 120. Rest ECG are the results of the patient's resting electrocardiogram. So it's on a scale of 0 to 2. The variable thalach is the highest heart rate the patient achieves during exercise. If this is very, very high, if the heart is beating very, very fast during exercise, it's probably not that good of a sign. Then the variable is exage. This indicates if the patient experiences chest pain induced by exercise. Again, this is a categorical variable. It either takes values 1 or 0. 1 means that the person does experience chest pain induced by exercise. 0 means that they do not. The next variable is old peak. So, old peak and slope are actually the results or variables which are related to the cardiogram of a person, which might look something like this. So, this the amount of segment means that there is actually a segment between the fall of a cycle and the beginning of the next cycle. So you don't need to know this in detail, but it just related to this electrocardiogram over here. So old peak is the amount of the depression induced by exercise relative to rest in this graph. Slope is the slope of the segment during peak exercise. It has a scale of 0 to 2. Then we come to the next variable, which is CA. So CA are the number of blood vessels which light up under fluoroscopy. So when the fluoroscopy is conducted, we check how many number of major blood vessels light up, and it has the scale of 0 to 3. Last two variables are thal, which are the results from the thallium heart scan. If 3, it's normal. If 6, it means fixed defect. If 7 means it's the reversible defect. And HD is the final variable. It's the diagnosis of the heart disease. So 0 means no heart disease is present, and 1 means heart disease is present. So this is the final target variable which we have. So there are 13 variables which we have collected for every single patient, these 13 variables. And the final goal is to predict whether that person will have a heart disease or not. This is the data set. Just to give you a visual of how our decision tree might look like, this is something what our decision tree might look like towards the end. It might be huge, it might be smaller, we don't know right now. But our goal is to construct a decision tree like this. So I hope you have understood or rather you're following with me until the first step, which is understanding the data set. Now let's go to Python and let's code out the first step. Before we move further, there are a number of things which have been written here, such as importing data, missing data, formatting the data, building a preliminary tree, optimizing the tree. We'll be following all these steps in a sequential manner. So let's first start out with importing the packages. Before we even start running or seeing the data set in Python, we definitely need to import certain packages. And there are or rather four go-to packages for decision tree codes. Those are, of course, pandas, numpy, matplotlib, and scikit-learn. Pandas is for loading and manipulating data and also for one hot encoding. NumPy is to calculate the mean and standard deviation. Matplotlib is to draw graphs. And the major package or the major library which is going to be doing all of the heavy lifting in this code is going to be scikit-learn. Through scikit-learn, we are going to import several different functions such as decision tree classifier, plot tree, train test split, cross validation score, and confusion matrix display. This is the advantage of these libraries, which have become so popular and so robust now that you don't have to write too much code yourself if you know how to utilize these libraries effectively. Okay, so I'm going to go ahead and run this piece of code right now, and it's implemented now. If you are running this for the first time, it will take some time. And one more thing to note is that you will need Python 3 installed and have at least these versions for each of the following modules. Pandas version should be greater than 0.25.1. NumPy version should be greater than 1.17.2. Scikit version should be greater than 0.22.1. So please make sure these requirements are satisfied before you run the code. Now, if you have installed Python 3 with Anaconda, you can check which version you have with the command conda list. And if, for example, your version of scikit-learn is older than 0.22.1, the easiest thing to do is just update all of your Anaconda packages with this command, conda update all. But if you only want to update scikit-learn, then you can also run this command, conda install scikit-learn, and give the version number which you want to install. So I hope this initial step is completed where we have imported the packages which are necessary for us to run this program. Now let's go to the next step where we will be importing the data. As I already told you, our entire data set is going to come from this UC Irvine machine learning repository. So what I have done is that I have actually gone here and I have downloaded the heart disease data. So you can go here, click on the heart disease, and you can actually download this data, download as a CSV file. Once you do that, what you can do is that you can just do pandas.read CSV processed cleveland.data. So this is how the CSV file will be downloaded on your machine. And one more thing to note, which has been added in the comment section here, is that it's also possible to download the data entirely from the University of California Irvine repository. So you don't even need to download the CSV file. But if you give this link here, then the entire data will be loaded for you. I'll be sharing this code file with all of you, so don't need to worry. All of this will be available when you receive this notebook. So I'm going to run this code right now. And we have already looked at step one, which is understanding the data on this whiteboard over here. But now let us try to understand the data through code. The first thing which I always do and which has also been done in this code is to print out the first five rows of the data set before anything else, just to see what we are dealing with here. One more note is that we are using pandas because it converts the data set into a nice table. So this command df.head, df is our data frame. Df.head prints out the first five rows of the data set. So let me run this. And you can see that the first five rows of the data set have been printed out. You can see that 0, 1, 2, 3, 4, dot, 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 up to 13. So there are 14 different variables here. Out of this, the first 13 will be the attributes for a patient. And the last variable here is the prediction, whether the person will have a heart disease or not. So you might be thinking, what is this 0 to 1? So I'll come to that. No need to worry about that at this moment. There is one way in which this table can be formatted nicely, right? So currently, every column just has numbers. So instead of numbers, it will be good to have nice column names. For example, instead of 0, it will be good to have age. Instead of the last variable just 12, it will be good to have thal, which is the thallium heart scan. Similarly, for 13, it will be good to have HD. HD is heart disease, so it's the diagnosis of the heart disease, right? So what we can actually do is we can specify to pandas what's the name of the columns. So we can say that my data frame has columns and the name of these columns are age, sex, CP, rest, BP, dot 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 up to HD. So let me run this and then I'll again print the first five rows. So if you run this, you will see that now the table has been updated. All the values, of course, remain the same, but the title of the column is now not 0, 1, 2, 3, 4. It's what we have defined over here. So this makes it actually much easier to manipulate the data. My experience with data sets and machine learning frameworks is that most of the time has to be spent on data, which is the boring stuff usually, right? You directly want to go to the model, do the testing, etc. But the real strength of a machine learning engineer or a data scientist is what they do with the data. And all of these steps which I'm showing you right now are very, very important. So here we can see the first five rows and just look at first row. So the age is 63, the sex is 1, which means male or female. CP, we have already seen what each of these means, right? So now CP is the type of chest pain for this person, it's type 1. This is resting blood pressure, this is cholesterol level. FBS means if their fasting blood sugar is greater than 120. Here for this person it looks like it is. So if you actually understand what these variables mean, when you look at a row like this, you will get a fair sense of the patient and how they are generally doing. This is good for intuition building. So that means you are not just a robot who is just looking at the data, but you actually understand what's going on. Okay, so now we have completed the first step and we have completed this first step in code also. So now we'll be moving to the second step. In any machine learning or data scientist or data science project, when you deal with real life data, you always have missing data, which means that let's say when these people are conducting this research, right, and when they are collecting the data, what if the nurse or the doctor forgot to write down the age of the patient, or what if for a particular patient they forgot to write down the slope or the fasting blood pressure, or they forgot to take the thallium scan itself. So we don't have the thal variable, we don't know what happened in the thallium scan, or they forgot to do the fluoroscopy. So we don't have the CA value, so we don't have how many blood vessels lit up during fluoroscopy. This may happen in real life, right? uh, People make mistakes and no data set is perfect, so of course there will be missing values when you deal with real life data, and we have to deal with missing data. We'll see how to deal with missing data in step 3, but in step 2, first we have to identify which data is missing for how many patients for which variables. So let's see how to do that in code. So step 2 is identifying missing data, and as Joshua has also written here, the biggest part of any data analysis project is to make sure that data is correctly formatted. So we have to deal with missing data. First, we have to identify missing data. Once we identify missing data, there are usually two ways to deal with it. The two ways to deal with the data are that we either remove the data for that particular patient. So, if for one patient some data attributes are not being collected, we either remove the data, which is of course the easy way out, but also the lazy way out. There is another second method to this, which is called as data imputation. What this means is that if you have the data from date of age of, let's say, all the patients, but two people are not there, one way is that what you can do is you can just take the mean or the average of all the data, and for these two people you say that instead of removing their that entire row of data itself for these two people, you say that their age is just equal to average, just as a placeholder value. That is called as data imputation. So these two methods are there to deal with missing data. But as I said, first we have to identify the missing data itself. So let us look at our data frame and let us see the types of data. So I'm going to run this command right now and you will see the types of data over here. So age is float, that's fine. Sex is float, that's fine. CP, which is chest pain, is float. Resting blood pressure is float 64. Col, which is cholesterol level, is float 64. FBS, all of these are fine. Up till here, they are float 64. Where you should be suspicious is when you see something like object. So when you see the type object, right, this is an indication that something funny is going on here, because if there are usually uh, two or three more data types in a row, um, then Python usually gives the type as an object. So for example, the CA variable was an object, right? So it may contain some numerical values, but it may also contain some empty values or some question mark values. So if this variable contains these different types of values, when you print the D type, Python will not say float, Python will say obj or object. So here you can see that Python has told this as an object data type, right? Which is the first indication that these two rows, CA, let's see what CA and thal actually mean. So CA means number of blood vessels which lit up under fluoroscopy, and thal is thallium heart scan. So for CA and thal, the data type is object. So this means again something funny is going on. Maybe there is missing data in these two rows. So let's check that out. So the way to check that out is you print out the unique values in the column called CA. So data frame CA dot unique. So let me run this. When you run this, you will see the unique values. It has 0, 3, and 2. That is fine because it's the number of blood vessels which lit up under fluoroscopy. But you see there is one more value here, which is the question mark, which means that for maybe many people or for some people, the fluoroscopy test was not done, and so it consists of the question mark over here. Great. So which means that the numbers, uh, which means that there might be missing data. The question mark definitely represents missing data in the CA values. Now let's look at the unique values in the thal, which means thallium heart scan. So if you print this data frame thal dot unique, you will see that it contains 6, 3, and 7. So 6, 3, and 7 definitely makes sense because 3 is for a normal scan, 6 is for a scan with fixed defect, and 7 is for a scan with reversible defect. That's fine, but there is a question mark over here. See, this indicates that again there is some sort of an issue which is happening here. There is a it suggests that the thalliums can also contain some mixture of numbers and question marks. So this also has missing values. So we know that out of this entire data set, there are two variables which have missing values, the CA and thal. So this is the result of step 2. After step 2, we have identified that there are two variables, the fluorescence, the fluoroscopy test, and the thallium heart scan. This kind of makes sense because both of these are tests, which means there is a lot of human intervention required, and that's why probably there is missing data for these people. So always at each step, try to add your intuition along the way. This makes machine learning less of a black box, and it's more like shining a torch on this black box. So step 2 is done, right? We have identified the missing data. Now we come to step 3. So step 3 we shows that we have to deal with the missing data. And I already told you the two ways of dealing with the missing data. We can either remove the data for for those people for whom the data is missing, or we can just impute the data, which means we can replace missing values with some sort of average. One good way to make this decision is to first find out of the total number of patients for how many people the data is missing. If it's just 1% or 2% or 3%, we can just remove it because it does not matter. We can retain the remaining 96 or 98%. But if it's 10 or 15%, then we definitely have to impute the data. So let's get started with dealing with the missing data. So now what we are doing is we are going to print the number of rows which contain missing values, for us to get a sense of how many patients do the CA value and the thallium scan value are missing. For how many patients have this question mark over here. So what we are going to do here is that we are going to use df.lock. So lock or LOC short for location. It lets us specify which rows we want. So here we are basically saying give me the total number of rows which have a question mark in the column CA or a question mark in the column thal. So first find out rows which have a question mark in the column CA, find out rows which have a question mark in the column thal, and then give me the length, which means that if there are three patients for whom thal is missing, if there are two patients for whom CA is missing, this function which we are printing here, it will give me an answer of 3 plus 2, which is equal to 5. In short, it will give me a length of how many patients have either thal missing or CA missing. So let me run this right now and it shows 6. So here we conclude that there are 6 rows which have missing values. So let's actually print out the rows that consist of the missing values. Here you can see there are 6 rows which have the missing values. The ID of the patients have also been written over here. Patient number 87, patient number 166, patient number 192, 266, 287, and 302. If you look at these patients, if you look at patient 87, for example, the thal value is missing. If you look at patient 166, the CA value is missing. Patient 192, again CA value is missing. Patient 266, thal value is missing. Patient 287, the CA value is missing. And patient 302, again the CA value is missing, right? Which means that there are 6 patients for whom either one of these values is missing. And now let's count the total number of rows in the data set, which means the total number of patients we have. This we should have done ideally earlier at the start of the data, but it's fine. We can even see it over here. So there are 303 people, right? So you can see this in the data set description also. So if you run this, you will see that 303 patients were there. Overall, we conclude that 6 of the 303 patients, or 2%, contain missing values. So even if we remove these 6, we'll still have 296, and that's plenty of data to build a classification tree. So here we will make the decision that we will remove the rows with missing values instead of trying to impute their values. It's just easier to remove these values because it's a very less number. It's just 2% of the entire data set, right? So it's fine. We can remove them and deal with the 98%. One thing to note here, which Joshua has also added, is that imputing missing values is a big topic. So we are not going into details about that here. Just a quick framework to decide which one is better, removing the values or imputing. In this case, it's totally fine to remove these rows. So we are removing those patients for whom the thallium scan was not done or the fluoroscopy was not done. So imagine there are 6 people who went to give their data, but unfortunately their thallium scan was not done properly. The fluoroscopy was not done properly, so there are missing values, and unfortunately these people won't get to be a part of our modeling, and that's fine. So we remove the rows with the missing values by selecting all of the rows that do not contain question marks. So what we are going to do is now we are going to look at the data frame and we are going to look at all those locations where the CA and the thal values don't have question marks. And we are going to call this DF no missing, which means that DF no missing does not have any missing values or does not have any question mark values. So if you print out the length of DF no missing, you will get 297. Great. Uh, we can make sure that the CA values and thal values in DF no missing indeed do not contain any question mark. So let's run the unique commands again. So I'm going to run this right now, and you will see that it has 0, 3, 2, 1, but it does not have question marks like it had before. Great. Then we run this also, the thal, and here also we see that it contains 6, 3, and 7, but it does not have the question mark values like it had before. That is awesome for us, which means that DF no missing. So we have verified that DF no missing does not contain any missing values. One thing to note is that CA and thal still have the object data type, if you must have seen over here, and that's fine because we are now ready to format the data because we have made sure that there is no missing data now. So even if the data type is object, it's fine. Great. So until this stage of this video, we have reached step number 3, which is dealing with the missing data. So let me put a tick mark next to all of the steps which we have completed in this video so far. Yes, so step number 2 has been completed. Oops. Step number 2 has been completed. Step number 3 has been completed. So we have identified missing data. We have dealt with the missing data. Step number 4 is to split the data into dependent and independent variables. So first let me explain this step on the whiteboard before actually moving to the coding part. So we have 13 variables which are the independent variables, right? Which are the x data which will be used to make the prediction. And this one variable which is now called hd, that is the y data. This is basically whether the person has the heart disease or not. And this is just one variable. So that is the y data. And all my 13 variables are going to be the x data. So now we need to split this data set which we have into dependent and independent variables. Because when we model the decision tree, we need to tell what's the x data, what's the y data, right? So let's go to the next step, which is split the data into dependent and independent variables. So the first step is to split the data into two parts. The columns of the data that we will use to make the predictions. So this is of course the x, and the columns of the data which we want to predict, which is the y value. So we will use the notation of x basically to represent the columns of the data that we will use to make the classification, and we will use y to represent the thing which we want to predict. In this case, we want to predict HD, right, which is the heart disease. Now, what we do over here is that we take the df no missing and we use this pandas command called drop. So df no missing dot drop. So we drop the HD column, which is the heart disease, which is the last column. So let me show this to you visually. So this was our data, right? We don't need this column in the X because that's our prediction. We want to predict whether heart disease is there or not. We only need these many 13 columns. So we are going to drop this column from the data set for the X, for constructing the X data. So X is df no missing dot drop, and we drop the variable named HD. It's very important to use this dot copy here, because if we not don't use copy, then by default pandas will use copy by reference. And if you do copy by reference, it's a lot of trouble, because if you make changes in one variable, it will make changes in other variables also, so it's very difficult to keep track. It's always much better to copy the data by value instead of copying the data by reference. If you don't know about copy by value and copy by reference, no need to worry. In this part, what we have done is that we have just dropped one variable, which is the output variable, so that we construct the x, which is just the training data. Or rather, the better way is to call it the um independent variables. So there are 13 of these variables over here, which is now my x data. Similarly, for the y data, what I'm going to do is that just look at one column which is named as HD, that is my y data. And this is the column where the person either has a heart disease or they do not have a heart disease. So note that now that we have created X, which has the data we want to use to make the predictions, and Y has the data which we want to predict, we are ready to continue formatting X so that it is suitable for making a decision tree. So let me now tell you what that formatting means. So we have completed step number 4 now, which was a pretty simple step, right? It was essentially converting or splitting the data into dependent variables and independent variables. Now we move to step number 5, which is one hot encoding. So before I show that to you in the code, I first want to explain this to you in some detail, because not many students actually understand why one hot encoding is done in the first place and why it is important. So, in my view, there is one very important reason to do one hot encoding, and that I will explain right now. So, one thing to remember is that one hot encoding is done for categorical variables. What I mean by categorical variables is variables which can only take certain values. For example, let's look at the categorical variables in our data set. Chest pain or CP is a categorical variable. It takes values. Let me use a different color here. So it takes values only 1, 2, 3, and 4. So it is a categorical variable. Rest ECG. So rest ECG is basically the resting. So let's see the definition of rest ECG. Uh, Rest ECG is the results of the patient's resting electrocardiogram, and it's on a 0 to 2 scale. So this takes the values of 0, 1, and 2. So that's why it's also a categorical variable. Then comes the slope. Slope is basically the ST depression slope in the electrocardiogram, and it takes values 1, 2, or 3. So it is a categorical variable. Then thal is the thallium scan, right? And it takes values 3, 6, or 7. It is definitely a categorical variable. And there are three more categorical variables: sex, FBS, which is fasting blood sugar, and exange. So let's see what exange is again. Uh, Exange indicates if the patient experiences angina. So it's either 1 or 0. So all of these last three variables, right, the sex, FBS, and exange, they either take values 1 or 0. So they are definitely categorical variables. Now, we cannot feed these categorical variables directly as this is in the model, and the reason is because imagine if you feed the CPU values 1, 2, 3, and 4, right? Um, the main issue is that let's say one person has CPU value of 4, and if the another one has 2, another one has 4, and another one has, let's say, 2. What our model might try to do is that it might think that there is some mathematical distance relationship between these. So 1 and 4 have a difference of 3, right? And 1 and 2 have a difference of only 1. So the model might think that patient 1 and patient 2 are somehow related to each other, or they have some similarities which are much more than the similarities between patient 1 and patient 4. So the difference between 1 and 4 is 3, and the difference between 1 and 2 is equal to 1. So the model might take these distances into account while making its predictions. But on the other hand, we know that these distances don't mean anything. In fact, the CP value is just a number between 1, 2, 3, and 4. It's just a category. If there are two people with CP value 1 and 2, it does not mean they are somehow closer to each other or they have similarities than if there are two people with CP values 1 and 4. And this is true for all these categorical variables which we have mentioned over here. There does not have to be, or there should not be, any distance relationship between each of these values. And the best way to avoid this is to one hot encode all of these values. So one hot encoding is actually very simple. Let's say if you look at the CP value, right, it is 1, 2, 3, and 4. So then you construct vectors of size 4. So 1 will be replaced by 1, 0, 0, 0. 2 will be replaced by 0, 1, 0, 0. 3 will be replaced by 0, 0, 1, 0. And 4 will be replaced by 0, 0, 0, 1. So if there is a patient with CP value of 3, it will be represented in the data set as 0, 0, 1, 0. If there is a patient with a CP value of 1, it will be represented in the data set as 1, 0, 0, 0. If there is a patient with a CP value of 4, it will be represented in the data set as 0, 0, 0, 1. Similarly, you can see for REST ECG. REST ECG takes 0, 1, and 2, right? So every vector will only have length 3. So for 0, it will be 1, 0, 0. If REST ECG value is 1, it will be 0, 1, 0. If REST ECG value is equal to 2, it will be 0, 0, 1. And we will proceed like that for the slope as well. It takes 3 values. For thal, it takes 3 values. So one out encoding is similar. For these variables, sex, FBS, and exange, they anyway take either 0 or 1. So we don't need to separately one hot encode them. So do you see how different this is than just from using the integer values? If you encode them as vectors, there is no distance relationship between them, since these are just vectors with either one value, only one value as 1. So all of them are on the same level now. There is no mathematical distance relationship. And it turns out to be extremely important to do this, especially for decision trees. So we are going to do one hot encoding for these variables for CP, for REST ECG, for slope, and for thal. We'll not be doing it for sex, FBS, and exange because anyway they have value 0 or 1. So you can think of it like they're already one hot encoded. Now let's move to the coding section. Here, Joshua has mentioned this in extreme amount of detail, what I just mentioned on the whiteboard over here. So essentially, what you do is that we first look at the data types again. So age, rest BP, cholesterol, and thalage are all float 64. That's fine. They are floating point numbers. Uh, so they are not categorical variables, right? All other columns of this data set, however, need to be inspected to make sure they contain reasonable values, and some of them need to change. The main reason is because scikit-learn decision trees natively support continuous data like resting blood pressure, and maximum heart rate, but they do not natively support categorical data. This is very important. So for CP, for example, as we saw, it's a categorical data. So we need to one hot encode this categorical data. So let us see how this is done in code. So first, if you do xcp.unique, it will print out the unique values in CP, which is 1, 2, 3, 4. This is exactly what we had seen over the whiteboard. So if you scroll up to CP, you will see that the unique values in the data set are 1, 2, 3, and 4. So the command which is used in Python actually to convert this into one hot encoding is called get dummies. So what you can do is you can type pd.getDummies x and you mention the columns which you want to one hot encode. So what this command will do is that it will retain all the other columns which come before this column, but that column it will put at the end and it will convert it into a one hot encoded format. So let's see how this is done. So I'm going to run this right now, and let's look at the, I have printed again dot head. So I'll print the first 5 rows. So if you see, all of these variables remain the same, but now let's look at CP. What we have done is that instead of only having one column for CP, now we have 4 columns. Because remember, this CP, when you one hot encode, it will be a vector of size 4. And then these are called cp1, cp2, cp3, and cp4. And then we have values. So for the first, it's true, false, 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 which means the cp value for this person is 1. For the second person, it's false, 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 and last one is true, which means the cp value for this person is 4. For the third person, it's false, 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 and true, which means again the cp value for this person is 4. For the fourth person, it's false, false, true, false, which means the CP value for this person is 3. For the fifth person, it's false, true, false, false, which means the CP value is 2. You can see this is a one hot encoding is done. And now we are going to do the similar thing for the 4 variables which you mentioned over here: CP, rest ECG, slope, and thal. So we are going to do the same thing. We are going to use pandas pd.getDummies, and we are going to one hot encode CP, rest ECG, slope, and thal. This new x which we get, we are going to call as x encoded. Okay. So let me print out x encoded right now, and let me print out the first 5 rows. So you see CP has 4 values: 1, 2, 3, 4. Rest ECG has 0, 1, 2. Slope has 1, 2, 3, and thal has 3, 6, 7. This is exactly the same thing which what we had written in on the whiteboard. Instead of having one value for all of these, now we are creating vector representations and we are doing the one hot encoding. One thing which again I have mentioned here is that for these variables such as sex, FBS, and exchange, they only have 2 categories: 0 and 1s. So we don't need to, we don't have to do anything special to them. You can think of them as already being one hot encoded. Okay, now before we move to the modeling part, there is one last thing which is remaining is that if you look at the Y data, right, which is the whether the person has heart disease or not, and if you plot Y dot unique, it will have 5 values. It will have 0, 1, 2, 3, 4. So it's the index up to which whether heart disease is present or whether it's not present. So 0, which means heart disease is not there, but it also has the level of how severe it is. So in this tutorial, we are doing a simple tree, and we only care if someone has a heart disease or not. So if the number is greater than 0, we can just convert all of it to ones, so that we just have 0 or 1. We don't want a 5 class classification right now. It will be very complex for this tutorial. So we'll just have 0 or 1. So if the y values are actually greater than 0, we are going to put all of them to be equal to 1. That's all. And then so the y values will only contain either zeros or ones. 0 means that heart disease is not present, and 1 means that heart disease is present. So let me run this right now. Done. So now the entire formatting is done. So you can see that I have spent so much time right now on just the data fine tuning, the data formatting. So now finally, um, we have completed step number 5. So there are total 10 steps in this tutorial. Out of this, 5 steps are dedicated only to manipulating the data, cleaning the data, dealing with missing values, understanding the intuition behind the data. It is very, very important for data engineers and machine learning engineers to do this step. You could directly jump to step number 6, which is building the classification tree. But it will be a lot of rework because then you will need to do the one hot encoding. Maybe there are some missing values, so you will get an error. So please make sure that you have to do this boring or non-fun part of dealing with the data. It is probably the most important distinction between a not so good ML or data scientist engineers and very good ML and data scientist engineers. Please keep this in mind. All right. So let's start building the classification tree now. We have done a lot of hard work in the previous 5 steps, and we have loaded the data, we have formatted the data, we have dealt very well with the missing data, and now we have come to step number 6, which is building the classification tree. So let's get started with this. Remember that all our data is now stored in this variable which is called x underscore encoded. So this has the one hot encoded variables. Remember that we have done one hot encoding for CP, rest ECG, slope, and thal, which is the thallium scan. Okay, so the first thing which we are doing is x train, comma x test, comma y train, comma y test is train test split x encoded, which is from the data. It will split into the training and the testing parts, and we are using a random state of 42. This random state will ensure that the code which I am showing you right now will be the same the way it runs on your machine. The initializations, etc., will everything will be the same. So here you might be thinking that what about the ratio, right? Where is the ratio mentioned here? So here we are going ahead with the default ratio. If you don't mention anything in the split ratio, Python, the scikit-learn train test split automatically assumes it to be 70-30 ratio. So 70% of the data will be in X train and Y train, and the remaining 30% of the data will be in X test and Y test. This step is a pretty standard step which is done in most of the machine learning frameworks, such as even regression, classification, and even deep learning tasks like neural networks. The reason this step is implemented is because it's not enough to get a good training accuracy. As we'll soon see, it's very important to make sure that we are doing well on the testing data as well. So now the main function which actually builds the decision tree entirely for you is called as the decision tree classifier. So you can actually search this in scikit-learn. It's probably one of the most widely used functions by machine learning engineers now, and this will provide you all the different things which you need. So here you can look at the different things which you can provide. You can give the criteria, you can provide the max depth, you can provide max features, you can provide max leaf nodes, you can provide minimum samples in the leaf. You can do so many things in the decision tree classifier when you initiate an instance of the class. For now, the only thing which I am giving here is the random state equal to 42, nothing else. We are going to look about some of these things like the criteria just in a minute. And then what we are going to do is we are going to use dot fit. So we first initiate an instance of this class and create a variable called clf underscore dt, which is classification decision tree. And then using this, we fit x train and y train. That's it. This one simple line will fit the decision tree. Now, one thing which you must know is that so when we build this classification tree, we are going to be using this command decision tree classifier dot fit x comma y. If we don't specify the criteria which is to be used, then by default the criteria which will be used by the algorithm for the decision tree classification is Gini impurity. We have covered a separate lecture in this series which covers everything about Gini impurity, which I'm calling GI here, and another criteria which is called as entropy. So here we are using Gini impurity by default. This criteria actually helps us to move in the right direction. If the impurity is very high, it means that the classification is not that good. So we generally want to move towards a low Gini impurity score. To give you one more point of intuition, Gini impurity is the best when there are no mixtures of classes. So in a leaf, if there is 100% yes or 100% no, it means the leaf is fully pure. But if the leaf has 50% yes, 50% no, it means the leaf is completely impure because it's like a coin toss. We are not sure either which way is preferred. The mathematical formula for the Gini impurity is 1 minus probability of yes whole square minus probability of no whole square. And if you are not familiar with this, it's fine. Right now, to understand this tutorial, it's not needed. Just remember that it's the criteria. But if you want to understand decision trees completely, I highly recommend you to watch the lecture on Gini impurity. So here you see the criteria. By default, it's chosen as Gini by the decision tree classifier. You can also give it entropy. So you can give entropy as the criteria, or you can give log loss as the criteria. Some other things in this function are something called max depth, then minimum samples in the leaf. These all criteria are to prevent overfitting. So generally, you don't want very few samples in a leaf, because which means that the leaf is terribly overfit. So currently, we are not providing any minimum samples. We are just going to keep it equal to 1, and you can feel free to explore with this notebook after I share it with you. Please try different things. So keep minimum samples equal to 3 and try to see whether the performance on the testing data improves. Ideally, it's better to have more minimum samples so that we are not overfitting. Another thing to avoid overfitting is mention some maximum depth of the tree, or mention the maximum leaf nodes, so that the tree does not just keep on growing and growing and growing and overfitting, right? So keep this in mind. I am not playing around with these parameters right now, because then this lecture will become too long. But note that all of this is possible to vary in the decision tree classifier function, which is given through scikit-learn. Okay, so now we are going to fit the decision tree. So let me run this piece of code. It's just 3 lines, and scikit-learn has made our job very easy. Now we can also use the plot tree command, which is given again through scikit-learn. We'll plot this classification decision tree, and here you can give the figure size. You have to also mention the class names such as no heart disease and heart disease. So let me run this right now. Uh, it will take some time to plot, but when you do plot, it looks something like this. It's a huge decision tree which we have constructed. This is our decision tree right now, and you can see there are a huge number of nodes. I'm not even going to try to count the number of nodes here. There are so many leaf nodes. But it seems that this is the decision tree which we have found. Clearly, when you see a decision tree like this, your first intuition should be that it's probably overfitting. We probably don't need these many leaves, because we are using the minimum samples in the leaf equal to 1. So there might be some leaf which just has one person in it. Who knows? This looks like a huge and a complex tree. But let's go ahead with it right now, and let's see the performance on the testing data. Remember what I mentioned, it's not just important to have training performance which is good, but it's also important to see how the decision tree performs on the testing data set. So we are now going to plot the decision tree on the testing data, and this is where we'll be looking at the accuracy. So I deliberately did not look at the training accuracy here, because honestly it does not matter too much. What's very important for us is the testing accuracy. So let me go ahead in the steps and right now mark the steps which we have actually finished. So step number 6. So we have finished step number 6, where we have actually built the classification tree. Now we are kind of moving to step 7. So we are in between step 6 and 7, where we are testing right now. So let's see. So to build the confusion matrix, we have to use confusion matrix display, which is again a command or a function given through scikit-learn, and we have to type dot from estimator. We have to give the classification decision tree, and we have to type in our x data and y test data. Remember, this is test data. So our tree, which is constructed right over here, will be evaluated on the x test, and we'll be comparing the values with y test. So let me run this right now. And when I run this, you will see that you get a confusion matrix like this. Okay, now if you have not dealt with confusion matrix before, let me show you a way about how to see the confusion matrix. So the first thing to do is look at this quadrant over here. So the predicted label is has heart disease, and the true label is has heart disease, which means our prediction is correct and our true label, it's matching. So there are 26 people who had heart disease, and we predicted also heart disease. That's great. That's the first quadrant to look at, in the green quadrant. The second quadrant to look at is the yellow quadrant. So here you will see that the predicted it does not have heart disease and the true label is also not having heart disease. So amazing. So we can clearly see that 31 people did not have heart disease and we correctly predicted that they do not have heart disease, right? Now let's look at the false positives. False positives are people who did not have a heart disease, but we predicted them to have a heart disease. This is shown in the blue label over here. So you can see that the predicted label has heart disease, but the true label is does not have a heart disease. So this is a false positive, and we have made 11 incorrect predictions here. And look opposite here to false negative, where the true label is that the person has a heart disease, but we have predicted that they do not have a heart disease. So there are actually 11 plus 7, which is 18 mistakes which we have made. Another way to look at this is that look at 31 plus 11. So look at the top row. It's 42 people who actually did not have a heart disease, right? Out of these, we have classified 31 correctly. So out of people who did not have a heart disease, whose true label was not having a heart disease, we have classified 31 correctly. So, which is 74% correct classifications for the people who did not have heart disease. Now, let's look at the bottom row, which is people who had heart disease, right? And we have classified 26 correctly. So, out of 26, 7 out of total 33, 7 plus 26, 33, 26 were classified correctly and 7 were classified wrongly. Their true label was that they had heart disease, but we predicted that they do not have heart disease. So 7 out of 33, which means that 21% were incorrectly classified or 79% were correctly classified. So overall, out of the people who did not have heart disease, our accuracy is 74% correct classifications. And out of the people who did have heart disease, our accuracy is 79%. The real question at this point, which you must ask yourself as a machine learning engineer or a data scientist, is can we do better? This is the question which you should, in fact, always ask yourself. Don't just reach this point and say that you are done, you achieved an accuracy close to 80%, and that's it. Maybe we can do something more to improve the accuracy. Maybe the tree looks very huge right now, right? Maybe we are overfitting. In fact, that's exactly what we are going to do. One thing that might be holding this classification tree back is that it may have overfit the data set. The tree has become very long. So, what we'll be doing is that we are going to prune the tree. In theory, pruning should solve the overfitting problem and give us better results. So, the first step is to identify that there might be overfitting and then to try to prevent that overfitting. This is exactly what we are going to do now. So we have now entirely finished step number 6, and now we are going to come to step number 7, which is preventing overfitting using cost complexity pruning. I'm not going to go into too many details about pruning, but I'll just give you enough intuition so that you will understand this part of the code. We have a separate lecture entirely dedicated to pruning in the decision trees from scratch series, so please go through that to deepen your understanding. When we consider pruning, what is done is that there is a tree score which is defined. The tree score is the total Gini impurity plus the alpha, which is the pruning parameter, multiplied by the number of leaves. So basically, if the total Gini impurity is high, the tree score will be high, which is bad for us. We eventually want to minimize the tree score. If the number of leaves are high, that also means the tree score is high. So that is also bad. So here you can see that it's not just enough for a tree to have low Gini impurity. The tree should also be smaller. We penalize if the number of leaves in the tree become too large. This penalizing factor is the CCP alphas, or right now let me just call it the pruning parameter alpha. So this actually reminds you a lot of regression, right? In regression we had the least square term plus we had a term such as alpha multiplied by modulus of theta whole square. The whole purpose of this modulus of theta was to bring down the weight parameters to prevent overfitting. Similarly, the whole purpose of this alpha parameter here and the number of leaves is that to bring down the number of leaves and to make sure that the tree is not gigantic, the tree is not very, very large. So, usually, the way this is done is that uh, each alpha corresponds to a prune tree. So, there is this thing called CCP alphas. When we run the pruning algorithm, there are some alphas which let me call as transition alphas. So these transition alphas are very important because as alpha goes on increasing, if you see here, if alpha becomes very high, the number of leaves have to be very low, right? Because then the tree score would become very large. So as alpha becomes larger and larger, the tree size becomes smaller and smaller and smaller. So uh, let's say the tree size currently is, so let me plot this. So let's say the tree size currently is, let me use a different color. Let's say the tree size currently is this, right? And then I'm constructing different trees which are pruned trees, and I'm plotting all of them here. And you can see that the tree size is reducing here. This is the tree size, or you can even think of the number of these as the number of leaves. The tree size is reducing here. Now, if you look at each of these trees, as the tree size is reducing, if you plot the alphas for each of these trees, you will actually see that as the tree size is reducing, the alpha values are actually going on increasing. So these are the alpha values which I am plotting here. So each tree size here corresponds to one alpha value. So these alphas are called as CCP alphas. CCP because cost complexity pruning. The method which we are using here is called cost complexity pruning, and the cost is just trying to minimize the tree score. The cost complexity is trying to minimize the tree score, and pruning, since we are trying to reduce the tree size. So if you look at this graph, as the tree size is reducing, for every tree size we get an alpha, and these I am going to henceforth refer to as CCP alphas, or cost complexity pruning alphas. Now we don't know which alpha is the best, so that is the whole exercise. We get these CCP alphas. Python gives us, scikit-learn gives us these CCP alphas, which are this list of transition alphas, but you don't know which alphas are the best. So you have to find the testing accuracy on each of these alphas. Remember, the higher the alpha, the shorter the tree. So there has to be a sweet spot. Maybe it lies somewhere here where the alpha is high enough but not too high that the test accuracy becomes very low. So now let's see how that is done. So we are going to implement cost complexity pruning now. So decision trees are notorious for being overfitting to training data set. And there are number of parameters like max depth, min samples, which I mentioned over here, right? Which you can definitely play with after this lecture is over. But today we are going to use cost complexity pruning because this can simplify the whole process a lot. So as I mentioned to you on the whiteboard over here, um, the whole process of pruning a decision tree is all about finding the right value of the pruning parameter alpha, which controls how little or how much the pruning happens. A higher alpha means that the tree is pruned a lot and the tree will be small. So one way to find the optimal value of alpha is to plot the accuracy of the tree as a function of different values, as we are going to do here. And these transition alphas, as I mentioned, are called CCP alphas. So cost complexity pruning alphas, or CCP alphas. So first we need to find these CCP alphas, and then we need to find the testing accuracy for each of these alphas. So let's go about doing that. So the way to find these CCP alphas is to take our decision tree, which is CLF underscore DT, classification decision tree, and use this function classification decision tree dot cost complexity pruning path, X train and Y train. What this function does is actually it determines those transition alphas at which the pruning happens. Remember, each CCP alpha corresponds to a different level of pruning, right? So these alphas are given by path.ccp alphas, and I'm storing them in a variable which is called as CCP alphas. So what is now done is that I'm going to create one decision tree per value of alpha, and I'm going to store it in the array. So remember, I mentioned each value of the decision tree corresponds to one alpha. So for every value of alpha in CCP alphas, I'm going to create a decision tree fitting between X train and Y train, and I'm going to store all of these trees in an array which is called as classification decision trees, plural. And I'm going to now do something very simple. I'm going to look at all the decision trees which are stored in this array. So let me actually write this on the whiteboard. So you have this array, right? And you have the decision tree 1, you have the decision tree 2, dot dot dot, maybe you have 20 decision trees over here. And each decision tree Let me use a different color here. Each decision tree corresponds to one different level of alpha. So alpha 1, this is alpha 2, maybe this is alpha 20. So what I'm going to now do is that I'm going to use each of these decision trees, and I'm going to plot the test data accuracy. I'm going to plot the test data accuracy for each of these decision trees. And I'm going to then choose the best alpha which we are going to use, which leads to the highest test accuracy. So this is what is done in the next plot. Here you can see I'm maintaining the training score, of course, for each of these decision trees, but I'm also maintaining the test scores. And I'm going to plot the train scores and test scores together in one plot. So let me run this right now. Okay, this is the plot which I get, and this is an extremely important plot, and all the engineers who are watching this tutorial or who are building decision trees on their own should definitely not miss this. 100% you should have this plot when you are evaluating decision trees. So let us try to understand this plot sequentially. The blue data is the training accuracy, and you can see that as alpha increases, training accuracy drops down. Why? Because look at the tree score. As alpha increases, the number of leaves need to be lower and lower, right, to give a minimum tree score. So the train accuracy has to drop down. And the interesting thing which we see here, if you look at the orange color, that's the test accuracy, right? As alpha increases, the test accuracy increases. There is a sweet spot over here, and if alpha becomes too large, then the test accuracy drops. So right over here where I'm hovering my mouse cursor right now, that is the sweet spot where the test accuracy is also very high, but the training accuracy is also high enough. Right now maybe we are here where the test accuracy is very high and the training accuracy is not very good. We need to be at the sweet spot where the test accuracy is the highest and the training accuracy is also not very bad. So in the graph above we can see that the accuracy for testing data set, which is the orange color, has the maximum value when alpha is 0.016, right about here. So this is the ideal alpha which we should be choosing. After this value of alpha, the accuracy of the training set drops off. So this suggests that we should definitely use the CCP alpha or the alpha parameter, which is equal to 0.016. Please keep this in mind. So now we have completed step number 7. Let me mark this with a green color following the usual convention. We have completed the step number 7 successfully. Now we move to step number 8. The main point of step number 8 is that for finding the best alpha, right now we did just used one training and testing data, right? But what if for different training and testing data there is a different value of alpha? So this plot which I showed you right now, right? We did the testing data accuracy for all these trees, but we just did it for one train test data. What if there is some other split which leads to a different value of alpha? Okay, so now we are going to implement cross validation. So this figure actually shows in a nice way what is done exactly in cross validation. In cross validation, what is done is that initially we split the data into training and testing, right? But in cross validation, now the training data is split into the validation data, and the remaining is used for training again. So this is a five-fold cross validation. So let's say you choose one value of alpha. You choose one value of alpha and you first have this as the validation set, then you have this as the validation set, then this and this. Each of this, you compute the error on the validation set. So this is E1, E2, E3, E4 and E5, and then you find the mean validation error. So this will make sure that you are using different data sets as the testing. So you will get one such error for one value of alpha. Similarly, for all the values of alpha, you will get different errors. And then you choose that value of alpha which gives you the lowest error. This is much better than what we did in the previous step. We just looked at one training and testing data set, right? The five-fold cross validation, what it allows you to do is that it allows you to use different validation sets, which makes sure that the alpha values which you are using are robust. So now we come to step number 8, which is cross validation for finding the best alpha. First, we want to show you a plot which shows that for the same alpha, if you have different training and testing sets, you have a different accuracy. So this plot shows that in the previous section we determined alpha to be 0.016, right? Now actually let's use this same alpha and construct training and validation sets. So what we'll be doing now is that we will be using alpha is equal to 0.016, and we will be constructing training and validation sets, right? And in each of these we'll be finding the errors, we'll be finding the validation error and the validation accuracy, and we are going to plot this. So here you can see, we in this graph we can see that for the value of alpha to be 0.016, the accuracy varies a lot using different training and testing data sets. So the graph above shows that using different training and testing data with the same alpha results in different accuracies, suggesting that alpha is sensitive to the data sets. So instead of picking a single training and testing data set, instead of picking a single training and testing data set, we'll do cross validation. So as I mentioned to you, in cross validation, what is done is that we first choose an array of alpha values and we calculate the mean validation error for each of these alpha, and then choose the alpha which gives the lowest error or the highest accuracy. So this is what is done here. So here is the array to store the results of each fold during cross-fold validation. So once the five-fold validation is done, the value will be stored in this alpha loop values. Okay, so the scores are stored in this alpha loop values array. So for each candidate value of alpha, we'll run the five-fold cross validation, and then we'll store the mean and standard deviation of the accuracy for each value of alpha in this alpha loop values array. So this is exactly what is done in this for loop over here. So what we are doing is that we first choose that value of alpha in CCP alphas. We construct the decision tree. Then we do the cross validation. We use this function which is called cross val score from scikit-learn, and then we plot the validation, or rather we store the validation accuracy in this alpha loop values. And what we then do after this is that we convert this alpha loop values into alpha results, and then out of this alpha results we are just going to plot the mean accuracy. So if you plot the mean accuracy for different values of alpha, we'll see that overall, instead of setting alpha equal to 0.016, the best value of alpha is actually 0.014. Here the cursor which I am at right now, that's the best value of alpha because it leads to the highest mean accuracy. So this suggests that instead of 0.016, the best value of alpha to choose is 0.014, and that is exactly the value of alpha which we are going to go ahead with. So the best value of alpha which we are going to choose is 0.014. It leads to a mean accuracy of 0.7477, and it leads to standard deviation of 0.09. So we have calculated the best alpha, which I am storing in a variable called ideal CCP alpha, and that's 0.014. So now we have chosen the best alpha, which was in step number 8. So remember, now we have finished step number 8, and it's important here to point out the distinction between step number 7 and step number 8. In step number 7, we just qualitatively saw which alpha value to use for one training testing split. But as we saw in step 8, different training testing splits lead to different accuracies for the same alpha. Hence, it's better to do cross validation when we choose the alpha. And for that, we use this function given by scikit-learn, which is called as cross val score. This will do cross validation as has been mentioned over here. This will do the cross validation, and then we'll be choosing the best alpha which gives the highest mean accuracy, and that we found out to be 0.014. Great. And now our best alpha has been chosen, right? So we can go to the step number 9, and step number 9 is testing the final decision tree using this best alpha. Now this is the very important step which we are going to be doing. So let's come to step number 9, which is evaluating and interpreting the final decision tree. So we have the ideal value for alpha now. So we can build the classification tree by setting CCP alpha So if you look at this decision tree classifier, there is a metric called CCP alpha. So you can build the classification tree by setting this. This will automatically prune the tree because remember each value of alpha corresponds to a specific level of pruning. So we will build the classification tree again, which is called classification tree pruned, and then we will use decision tree classifier. But now we'll add one argument here, which is CCP alpha is equal to ideal CCP alpha. Remember when we did this same thing over here, when we did this same thing when we built the classification tree, we did not put the CCP alpha over here, right? We did not put anything over here because we did not know what is the best alpha to choose. But now we know based on the cross validation analysis. So we can put the CCP alpha, it will be equal to 0.014. Great. And now let me run the same function, which is classification decision tree prune dot fit x train and y train. So let me run this now. And now let me actually uh, plot the confusion matrix once more. So here now we can see that, let's look at the top row. Out of 42 people who did not have heart disease, 34 people we are classifying correctly as not having heart disease, which is 81%. In the previous case, it was 74%. So there is a 7% improvement in accuracy. Look at the bottom row. In the bottom row, there are 33 people who have heart disease, and we are correctly classifying 28 of them. So in the bottom row, we have 85% which are correctly classified. In the previous full size tree, we are only correctly classifying 79%. So we have 6% improvement in the bottom row. In the top row, which is for people who do not have heart disease, we have an improvement of 7%. And in the bottom row, which is for people who have heart disease, we have an improvement of 6%, which is amazing. And we achieved all of this by actually just adding one parameter here, which is CCP alpha, because we pruned the tree. This is a very practical demonstration of why pruning works and how pruning is actually extremely useful to prevent the overfitting problem. One more amazing thing which I want to show all of you is, now let us actually plot the prune tree and let us see what it looks like. This is what it looks like. The first thing which you can see is that it's much smaller than the previous tree, right? This previous tree was huge and still it was giving a lower accuracy on test data. Now we used a prune tree with an alpha of 0.014, which corresponded to this level of pruning. And here you can even count the number of leaves: 1, 2, 3, 4, 5, 6. We have 7 leaves, and it's so easy to visualize this tree. In fact, I can even explain this step by step. So first we look at the CA score, right? What is the CA score? The CA score is basically fluoroscopy and illuminating the blood vessels to see how many are lit up. So if the CA score is less than 0.5, we see the thallium score. If the thallium, we see the thallium scan, and if the thallium scan value 7 is less than zero point 0.5, then we look at the old peak value. If the old peak value is less than 2.7, we can say that the person does not have a heart disease. Let's go to the other side. If the CA value is greater than zero point 0.5, which means that if when we shine the fluoroscopy, if the blood vessels are lit up after a certain potential, then you look at the CP value. Let's look at again what CP value is. I think it's chest pain. So if the chest pain 4, remember we are one hot encoding, so there is CP1, CP2, CP3, CP4. If that's less than zero point 0.5, then we can predict that the person already has a heart disease. So from these plots you can also see, or from this final decision tree, it's very small, so it's very interpretable, it's very simple to understand. This is one very important thing. Complex trees doesn't necessarily mean that you have achieved something great, because if you look at this complex tree, it is extremely difficult to really interpret what is exactly going on in this tree, which variables are important, which features are important. You cannot say at all, right? But if you look at this tree right now, we can clearly say that the CA value seems to be at the root node of the tree, so it's very important. The CP value shows up at multiple places, so that is another very important metric. The old peak value is very important. So from this decision tree, I can actually very easily conclude that from all these 13 variables which were there at the start of our problem, let's look at these variables. From these 13 variables which were there, so first let me rub some things so that It will make it easier, right? And based on the final decision tree, what I can say is that from these 13 variables, the CA variable is very important, the CP variable is very important, the thallium scan is very important, and the old peak are very important. I can say that these four variables lead to majority of the predictions or very important predictions in my decision tree. Because if you see the leaves, many of the leaves of this decision tree have either CA value, CP value, old peak value, or the thallium value. The rest of the values are not showing at all. And I could not make this prediction by looking at the complicated tree before. So now, based on this decision tree analysis, I have a much better understanding of the problem than I had before. I know that the type of chest pain the patient experiences is important. The old peak, which is the amount of ST segment depression in the electrocardiograph, is important. The number of blood vessels which are visible under fluoroscopy is very important. And finally, the results of the thallium heart scan are very, very important. So if a new person comes to me and if I want to check whether they have heart disease or not, I'll first check the CA score. If it's less than zero point 0.5, I'll check the thallium scan. If it's greater than zero point 0.5, I'll check the chest pain. And then I'll just follow these branches and then I can very easily predict whether the person has a heart disease or not. This is a beautiful example of using decision trees in practice, and it again shows that smaller trees actually are interpretable, and then it can give you a lot more information. One more thing which you should be noting here is that there are two values here, right, which is 118 and 104. So let's see what they mean. So let's discuss how to interpret the tree. So in each node there is the variable. So in each node, if you see, there is a variable such as here there is the CA value and the threshold for splitting the observation. For example, in the tree's root, we use CA to split the observation right here. All observations with CA less than or equal to zero point 0.5 go to the left, and all observations with CA greater than zero point 0.5 go to the right. Gini is the Gini index. So the second thing which is mentioned here is the Gini. Remember, we are calculating the Gini impurity. So for this, it's 0.498, which is actually pretty worse, because zero point 0.5 is the highest value of Gini impurity which you can ever obtain. But later the Gini impurity becomes better. So for example, here you can see it's 0.126, which is awesome. Here you can see it's 0.24, again amazing. 0.185, it's good enough. Samples tells us how many samples are in that node. So in the first node there are 222 samples. In the last node here you can see in the last leaf 87, 6, 20, 19, 18, 13 and 59. So let's look at all the leaves. Here in this leaf there are 87 samples. Here there are 6. Here there are 20, 19, 18, 13 and 59. This is good because, as I mentioned before, if some leaf only has one sample, it is not good. It may lead to overfitting. We cannot just have one leaf because one person belongs there. Then, which means we might be fitting just noise. Here we can see that all leaves have more than 5 samples. Most of the leaves have more than 10 samples, which is amazing. I'm pretty sure if you look at this leaf, which if you look at this tree, which is impossible to see right now, if I zoom in, here you can see actually there is only one sample. There are only three samples. So if you look at the leaf nodes of this tree, here you can see again one sample. There is only one sample in most of these leaves. That's why it's overfitting. Okay, then the last thing to look at is value. So value tells us how many samples in the node in each category. So in this example, we have two categories, no and yes, right? Referring to whether or not the patient has heart disease. The number of patient with no comes first because the categories are in alphabetical order. So here you see 118 people do not have heart disease and 114 have with this CA value. So here if you see again 98 and 34, which means 98 does not have heart disease and 34 does have heart disease. In fact, the orange ones, if you see, the class is no heart disease. And if the blue ones, if you see, they do have heart disease. So if you see this one, right? So 4 and 15, right? So here it means that 15 do have a heart disease and 4 do not have heart disease. So always the higher value here corresponds to the class name. So if here you see the class name is no heart disease, the higher value is 16, which means 16 people have no heart disease. Here if you see the class name is yes heart disease and the value higher value is 10, which means 10 people have heart disease. This is how to evaluate the value. The class tells us whichever category is represented most. So in this route, since 118 people have no and 104 have yes, the class is set to no. So here see 118 have no and 104 have yes. So the class is set to no. The class is always set to whatever the highest in the value is. So here if you see, the class is no heart disease, which means 98 people, which is more than 34, do not have heart disease. Okay. So lastly, the nodes and the leaves are colored by class. So you can see that the no is different shades of orange. Here you can see, here it's 16 and 15. So it's borderline, right? So it's slightly close to white. But the nodes which are extremely confident about being heart disease, yes. So the Gini impurity, the higher it is or the lower it is for yes heart disease, they will be dark blue, and the Gini impurity, the lower it is, it will be dark orange. So you'll see the darkest colors are for the lowest Gini impurity, and in general, the shades of orange are for class disease no, heart disease not present, and shades of blue are for yes heart disease is present. And as I mentioned, the darker the shade, the lower is the Gini score. And that tells us how much of the node or leaf is skewed towards the one class. So, for example, look here. This is the darkest orange leaf because it has the lowest Gini impurity. And this is highly skewed towards people not having heart disease, 78 versus only 9 people have heart disease in this node. Whereas, let's look at the darkest blue one. So, this is the darkest in the blue because it has the lowest Gini score in the blue, and here you can see 55 people have heart disease and only 4 do not have. That's why it's very highly skewed towards those who have heart disease. So there is a specific way to interpret this graph. Always look for colors, always look for the Gini score, look for the sample number, and always look for how many people are there. So look for the sample number in the root node, sorry, in the leaf node there should not be very few samples. That's actually a sign of overfitting. Okay, so now we have completed. Let me check how many steps we have completed. Okay, so just right now we have completed step number 9. And finally, after doing all this hard work, we come to step number 10, where I'll show the conclusion of what we have done so far in this lecture. So, in this lecture, we have essentially imported data, then identified and dealt with missing data, then formatted the data for decision trees using one hot encoding. Then we have built a preliminary decision tree for classification. It turned out that it had overfitting. It was a huge tree, and then in the leaf nodes, there are some samples which were just one in number. So we wanted to reduce the overfitting. For that, we used cost complexity pruning. Using cross validation, we found the best alpha, which we called ideal CCP alpha or cost complexity pruning alpha. And then using that alpha, we built the decision tree again. Then we tested the decision tree, and that was much smaller. And that, in fact, had much better accuracy than our larger decision tree. And it was very easy to interpret what's going on here. We identified the features in the heart disease dataset which probably carry the most importance, such as the CA value, how many blood vessels are lit up during fluorescence, the CP value, chest pain, the old peak, and also the thallium scan. All of these insights were very difficult for us to know at the start of this lecture, and now we have reached here where we've identified the key variables. Not just that, if any new person you encounter and if you collect all their variables, you just follow the logic in the decision tree and you can predict whether they will have heart disease or not. This is the beauty of decision trees. It's really an amazing topic, and it's very simple and it's interpretable. That's why it's much better than neural networks in that case, in that sense. That's why in many companies, machine learning, when machine learning algorithms are used, they have a very heavy reliance on decision tree based algorithms because they are interpretable like this. I want to point out two main things here. First, never neglect the data handling. So remember, step 1, 2, 3, 4, and 5, which we looked at, were all related to data formatting, data manipulation, and data imputation and data cleaning. It's very important to do these steps, and then you move to modeling. Even in modeling, don't be satisfied with the first testing result which you obtain. Always try to prevent overfitting. Use cost complexity pruning, use cross validation, and then keep on testing again and again and again. Finally, you can explore the decision tree classifier in Python. So what you can do is that without going into the cross validation or without going into overfitting, what you can try to do is that when we first train the tree, here itself you can add the different things, such as you can try adding max leaf nodes, for example. You can try adding max leaf nodes. You can try adding max depth, and just explore what is the kind of tree which you get. You can visualize the tree. You can also explore the confusion matrix, etc. This will really help you in understanding the code. The best way to understand the code is to run this many times and play around with the different parameters. So this brings us to the end of this lecture. It was a pretty long lecture, but I wanted to cover everything in detail. Again, this lecture is in reference to the this notebook from Stats Quest. So thanks to Joshua Starmer for sharing this notebook. And thanks everyone for going through this entire lecture. I hope you have a much better understanding of classification trees now. In subsequent lectures, we'll be looking at regression trees, and then we'll move to random forest and XGBoost. Thank you so much, everyone, and I look forward to seeing you in the next lecture.